Hello, I'm your host, Dr. David Urban, and I will be guiding you through Brown and Poon's Introduction to Organic Chemistry, 6th edition. The slides were downloaded from the Wiley Instructor Companion site and are copyrighted by Wiley. The commentary is my own. I have divided each chapter into smaller sections to make it easier to view on a wide variety of platforms. So let's begin. We will start with Chapter 4, Part 1, Alkenes and Alkynes. Okay, so in the previous chapter, chapter 3, we learned that we had what we called unsaturated hydrocarbons, saturated hydrocarbons, and unsaturated hydrocarbons. So all of the alkanes were what we call saturated carbons because they had no carbon-carbon double bonds or carbon-carbon triple bonds. But we did learn about the infix ene and yne. So an ene is anytime you have a carbon-carbon double bond in the formulation, and an yne is when you have a carbon-carbon triple bond in your formulation. So all of our alkenes have at least one double bond, and all of our alkynes have at least one triple bond, okay? So there's another form of unsaturated hydrocarbon that we're not going to talk about until chapter 9, and that's benzene and its derivatives. And this is a special kind of alkene where it's in a ring and has alternating single and double bonds. Because of this alternating single and double bonds, it has different reactivity than what we'll be describing in chapters 4 through 8. Okay, so even though we're not going to study this in chapter 9, we have to know about them because we can use it as a substituent. So the group itself, just by itself, is called benzene, but when it's used as a substituent on things that we'll be using in the alkenes and alkynes, we actually call it the phenyl group right here, and it's sometimes designated as C6H5 with a bond to it, or occasionally just a pH with a line here. So you might see that this phenyl group is represented in any of these things, but again, we aren't going to look at the reactivity of it until later. Okay, so the first thing we have to think about when we started thinking about the alkenes is the idea that the carbons are sp2 hybridized, meaning that they're trigonal planar. Okay, so the three bonds around that carbon are going to be approximately 120 degrees. Okay, now that angle gets slightly bigger when one of the atoms is bigger than the others. So in the case of ethylene here, the angle between the carbon and the hydrogen here is slightly larger than 120 degrees because carbon is a bigger atom than the hydrogen. Okay, this becomes even more pronounced once we switch out this hydrogen with a methyl group in propene, and we'll see that angle gets even bigger. So we have a big carbon butting up against a big carbon, making that angle even bigger than that 120 degrees wants to be. But overall, the carbons are approximately 120 degrees and they are trigonal planar. Okay, so the reason we can make this double bond is that we have three equivalent sp2 hybridized orbitals that make that trigonal planar structure, and we have that unhybridized p orbital. That unhybridized p orbital on each of those carbons overlaps with the one next to it to give us that double bond. Okay, so now that we have those p orbitals forming that double bond above and below that plane, we would have to break that pi bond to be able to rotate around that bond. When we had hydrocarbons, when we had the alkanes, those are sp3 hybridized, and we have free rotation around that bond. But because we have those pi orbitals, those p orbitals overlapping to make that pi bond, we no longer have free rotation. So our trigonal planar is structurally flat and does not have rotation over a double bond. Okay, what does that mean? If we do not have rotation over that double bond, that means when our substituents are on the same or opposite sides, they are stuck that way. Therefore, we have to consider that they have isomers. Okay, so if the two groups on a double bond are on the same side, we call this the cis isomer, just like the two substituents on cyclohexane. would be a cis isomer. And if they're on opposite sides, they would be called the trans isomer. Okay. Now, they don't flip back and forth with each other just like a cyclohexane or just like a regular hexane might rotate freely around here. And we know this because we can isolate them and they have different properties, different melting points, and different boiling points. And they even have different bond angles because of the strain. If we think about the cis having the two methyl groups closest together here, that's going to strain it a little bit more and give you a little bit different of a boiling point than if you had them on opposite sides here where they're not close to each other at all. Okay, so that double bond, that pi bond, is the thing that keeps it from freely rotating. And without free rotation, we now have isomerization. Okay. Now let's look at the alkyne, okay? So in the alkyne, the carbon is sp hybridized, meaning there are two p orbitals available to form pi bonds. And so one of the pi bonds will form in the x-axis opposite the main chain, the main axis of the hydrogen-carbon-carbon hydrogen bond. And then the other one will be on the y-axis associated with that. So if we looked at the hydrogen-carbon-carbon hydrogen bond as our z-axis, we have one pi bond in our x-axis and one pi bond in our y-axis. So when we look at a triple bond, we have one sigma bond for 2 electrons, and we have 2 pi bonds for 2 electrons each, bringing a total of 6 electrons to form a triple bond.